Okay. So, Aldo, do you want to present our speaker?
Yeah, I'm gonna read your CV a little bit, not that much.
Okay.
So it's gonna take me like 5 minutes, Carl. No, not.
All right. That
So
didn't work.
Carl did his bachelor's in physics in Reed College, I guess, and then he went for the PhD and grad student at Northwestern. There you work with Phil Rassio, right? With Fred Rassio.
Yeah.
At that point. Then he did a postdoc in MIT for I think 3 years, something like that. Then moved to Harvard, and I mean he got a lot of fellowships and awards during that time to actually support all the to fund all the investigations. And finally, he's a professor in Carnegie Mellon at Pittsburgh. So he's been working in formation of binary black holes, mostly in star clusters and then stellar systems. But he's been actually doing some other work that maybe we're going to hear about in this talk. So
Yeah.
the floor is yours, Carl.
Oh, thank you very much, Aldo. And thanks everybody for having me. I'm having a little bit of annoying trouble with my internet. Give me 1 second and I'll see if I can wrestle this into functional form.
Okay.
Okay, can people see the slides?
Yeah.
Okay, awesome.
Now we do, yeah.
All right, awesome. Well, yeah, thanks again for having me. And I'm really excited to sort of talk about some of the work that I've been doing for the past few years. And I always like to start with this plot because it really, I think, hammers home exactly how dramatically the field of stellar mass black holes and compact object astrophysics has changed just in the last 5 years. So around 2015, right, this is pretty much everything we knew about stellar mass black holes in the local universe. We knew that they came from about 5 to 15 solar masses. There were a couple of tentative detections above that. There were around 20 or 25 solar masses. But pretty much everything we knew up until that point, we knew about through X-ray binaries. So observations of a mass transferring system that emitted in these sort of hot X-rays from the disk. Of course, this whole thing changed in September of 2015 with the detection of the first gravitational wave event, which was GW 150914. And already, right, this thing has masses well above any of the black holes that we had detected through X-ray observations up till that point. And since then, of course, we've only detected more and more numbers of objects. So as of the middle of last year, this picture looked something like this. And we had already entered this regime where the majority of stellar mass black holes we had detected had been detected through gravitational waves. We also started to get observations of black holes detected through radial velocity measurements. So these were detached stellar mass black holes whose mass was inferred by the radial velocity of their companion. And so this was the picture as of last year. And as of the release of the last gravitational wave catalog from LIGO, the picture actually looks something like this. So this is the current sort of overarching view of stellar mass black holes that we know about throughout the local universe, at least as of last year. From what I hear, LIGO is also preparing to release the second half of their catalog, which should have another ballpark 30 or so binary black hole merger candidates in there. And that I think is happening this weekend, from what I've heard. I'm not a LIGO collaboration member, so I only have rumors and innuendo to go on. And so at this point, the majority of black holes that we know about have been detected by LIGO and Virgo, which is kind of an amazing turnaround from even just 5 years ago. But of course, LIGO and Virgo are not the only gravitational wave detectors that are currently operating or in the planning stages, right? We've also got the pulsar timing arrays, which are continuing to sort of reduce their overall noise floor and getting closer and closer to the detection of nanohertz gravitational waves and supermassive black holes. And then in around the 2030s, we're hoping to see the launch of the Laser Interferometer Space Antenna, a large constellation designed to detect millihertz gravitational waves of supermassive black hole mergers. And in the mid-2040s, although I actually need to update these slides because the number is closer to mid-2030s now, we're hoping to see the next generation of ground-based gravitational wave detectors, things with names like Cosmic Explorer, Einstein Telescope. And these detectors, through a large number of sort of technological improvements and sort of grander scale plans, are anticipated to detect compact object mergers, potentially up to redshift of 10 or even 20. And the thing is, we don't really expect there to be that many stellar mass black hole mergers beyond Z of 10. So there's a non-trivial chance that by the late 2030s, we might be in a position to detect every black hole merger everywhere in the observable universe, which is a pretty phenomenal thing to be able to say out loud. And so that's just sort of the introduction I like to give before getting to my actual title slide. And what I'm going to actually do is sort of back up a little bit and talk about a process that we still don't fully understand, which is how do you actually make these binary black holes in the first place? How do we produce the binaries, and particularly the merging binary black holes that have been observed by LIGO and Virgo so far? So to do that, I'm going to back up to this slide where I showed just the first gravitational wave event. And we're going to zoom in on it a little bit. So we all have probably seen at this point what the gravitational wave signal from this merger looked like. Here's the plot from Livingston and Hanford. And even though the masses were somewhat surprising observationally, we actually do, relatively speaking, know how to form a 30 solar mass black hole. You basically start with some massive star, and as long as the star has sufficiently low stellar metallicity, it's actually going to retain the majority of its mass as it evolves from the main sequence to the giant phase, and eventually collapses to form a black hole. And so as long as you're looking at stars that have essentially metallicities of about half or less that of the sun, it's actually pretty straightforward to form 30 solar mass black holes. The trick and the difficulty is actually getting them into a binary that will merge in the first place. And in particular, the trick is getting it into a binary that will merge within the age of the universe. Because for that process to occur, if gravitational waves are what is going to drive this binary to merger, I need to start these things off with a separation of about 0.2 AU. The problem is, during the giant phase, these stars expand dramatically, and with radii that are sometimes as large as 20 AU, or even larger, depending on the mass and some of your assumptions for stellar evolution. To scale, that would actually look something like this with the binary. And so you have to simultaneously solve this sort of problem of allowing these stars to evolve through their normal evolutionary processes, where they blow up to massive radii, but somehow ending up with the compact objects that they form in a tight enough binary to merge within the age of the universe. And so solving this sort of separation problem is one of the key details you have to get right in order to explain the binary black holes detected by LIGO and Virgo. And there's a couple of general ways that people approach this problem. The first is that you start off with a massive isolated binary. So just a standard stellar binary hanging out there in space. And you start it off with a sufficiently large separation that when the stars actually expand to be giants, they're not necessarily going to interact and merge during that phase. And so the general idea is as follows. I start off with my stellar binary. The more massive of the two stars initially goes supernova, or more likely directly collapses to form a black hole. The secondary can then expand on giant branch. And what we think happens is that this massive diffuse hydrogen envelope essentially envelops the entire system, and you end up with what we call a common envelope phase of evolution. And here, dynamical friction actually brings the core of the secondary and the black hole primary just close enough together to where they're almost about to merge, but not quite. And at the same time, that sort of dynamical friction injects enough energy into the envelope to eject it out into space. At this point, the core of the secondary can collapse to form a black hole, and I'm left with a binary black hole that, at least in theory, will merge within the age of the universe. In practice, of course, there's a lot of fine-tuning that's required to get this process to work just right. I need to basically bring the core of the secondary and the black hole primary just close enough together to where they will almost merge, but stop just short of that actual merger point. Because I need to actually be left with a binary black hole that still has some time to emit gravitational waves. And so because of that fine tuning, there's a lot of uncertainty in the sort of predicted merger rates of binary black holes. And in fact, you can visualize this uncertainty either in terms of the actual astrophysics, or you can visualize it in terms of the publication year of the studies that have looked at common envelope evolution. So this is what I'm plotting here is essentially several different predictions for the binary black hole merger rates from common envelope evolution as a function of publication year. And what you can see is that the median merger rate, even from the same code, has sometimes jumped by several orders of magnitude as even minute changes to the physics and the initial conditions are implemented in the code. In fact, one of the rates actually goes essentially from several hundred per gigaparsec cube per year down to a 0.1 per gigaparsec cube per year. So nearly a 3 order of magnitude change within just 5 years. And it's not that they're radically changing the physics in these codes. It's that it's a very hard problem with a large number of uncertainties, and very minute changes to the physical assumptions can dramatically change the output. Now you'll notice that at the end, the predicted merger rates all start to converge to a single value. And what's happening there, of course, is that after 2015, we started to get predictions for what the binary black hole merger rate actually was. And then you at least have some intuition of what parameters you need to choose to get to that binary black hole merger rate. Of course, what I've also done here is I've only picked the median rate, or whatever they call the most standard rate from each of these studies. In practice, each of these studies actually have a large amount of internal uncertainties where they explore all of the different physical assumptions that they put into these models in order to really parameterize the uncertainties. And so this is sort of the issue with common envelope evolution. It essentially could explain all of LIGO's binary black hole mergers, or it could explain none of them, depending on what assumptions you make about your initial binary populations, about your common envelope evolution, and more generally about mass transfer and how it affects the orbits of massive stars and compact objects. So this is sort of the main channel that people had looked at for many years, but there's a lot of physical uncertainty in this. What I'm going to do now is look at the other channel, one of the other main channels for binary black hole formation, and I'm going to argue that it actually has a significantly less uncertain sort of range of possible parameters and fine tuning that essentially make it a much more appealing formation scenario to study in a lot of ways. So if we go back to this picture of isolated binary evolution, I'm going to start off by completely dispensing with the pre-existing binary entirely. And I'm going to start off with just 2 massive stars that are unbound, that are initially unbound from one another. Now, at this point, right, there's no separation problem that I need to solve. So the 2 stars are going to evolve along their merry way and produce 2 black hole compact objects. But now I have a different problem, right? I somehow have to get these 2 black holes close enough together and into a binary to where they will merge within a Hubble time. Now, if I just have a 2-body encounter, sort of a standard hyperbolic encounter, right? I have a positive energy for the incoming particles. I'm going to have positive energy for the outgoing particles. There is no way in a purely Newtonian point particle analysis to get these 2 particles into a binary. I'm going to revisit the Newtonian assumption of that later on in a way that is that makes for some very interesting implications. But one way that I can form a binary is to essentially introduce a third object. So if I have a third object nearby, say a black hole or another star, what I can do is during this close paracenter passage of these 2 objects, I can essentially dump some excess energy and angular momentum onto that third interloping particle. And if I dump enough energy onto the particle, it actually can take me from a positive unbound energy state into a negative bound energy state for my binary. As you might expect, this process is very rare in the fields of galaxies. The stellar densities there are so low that this process is extremely rare over the evolutionary history of a single galaxy. But there are particular star clusters out there and dense stellar environments where this process occurs extremely frequently. And in fact, this process is actually necessary to regulate the evolution of some of these star clusters themselves. In particular, I'm looking at these particular class of systems called globular star clusters, which are typically very old, massive star clusters found in the Milky Way and most other galaxies. Now, this category of binary formation is sometimes called dynamical formation, and it really just is set up to delineate the sort of isolated binary channel from those where you rely on chaotic but well understood gravitational interactions to form these binaries. Now, I always like to present this as sort of two competing formation scenarios. In practice, there's a whole host of potential formation scenarios out there. And of course, theorists, we have to earn a paycheck somehow. So there's been a huge proliferation in numbers of theories for forming binary black holes since the first detection. But the real question that I'm interested in is, can we actually tell the difference of some of these formation scenarios? And so to do that, I'm going to dig a little bit more into the dynamical formation scenario and describe a little bit more exactly what some of the key predictions of this formation scenario are. So like I said, when I talk about globular clusters, I usually mean, or dense stellar environments and dynamical formation, I usually mean globular clusters. These are typically very old, low metallicity star clusters that are found in most galaxies, and they tend to be pretty massive. So anywhere from 100,000 to, in some cases, 1 million or more stars. And critically for our purposes, they're very compact with radii of usually only a few to maybe a few tens of parsecs. And so the central densities in these star clusters, particularly of the black holes, can reach as high as several thousands or even tens of thousands of black holes per parsec cubed. And like I said, these globular clusters are found in just about every galaxy. Our own galaxy has ballpark about 200 globular clusters in it. And that number scales with the mass of the dark matter halo. So more massive galaxies, like say M87, typically have tens of thousands of globular clusters. Now, when I start off with some initial population of stars, the most massive stars are immediately going to collapse into black holes. And at this point, I am left with what is essentially a textbook dynamics problem, right? I have a massive object that is traveling through a sea of stars with some velocity. And as it travels through that sea of stars, it's essentially going to gravitationally attract several of the field stars towards it. But by the time it moves out of the way, it will have built up an overdensity of stars behind it. So this overdensity essentially creates a preferential gravitational attraction from the field stars in whatever direction is opposing the velocity of the massive object, and essentially leads to this process called mass segregation, where the most massive particles are going to rapidly segregate into the center of the star cluster. Now, the exact timescale for this to occur depends on the masses of the black holes and the overall properties of the cluster, but for a typical globular cluster, this happens within about 100 meg-years. And now at this point, I have a centrally concentrated sort of core of black holes in the cluster that also typically has a high enough number density that these sort of three-body encounters that I was describing can occur regularly. And so I can have these three-body binaries come in, they can form a binary, and then I have essentially what is a problem almost more from collider physics than it actually is from astrophysics. Because what I'm left with at this point is a large binary with some semi-major axis in the middle of an environment where other objects are going to come in with some velocity and interact with it. Essentially, I've created a particle physics experiment where I have some target with cross-section given by the semi-major axis, and I'm going to bombard it with other particles from essentially a beam of stars. And in fact, if you're feeling particularly physicsy, you can even parameterize what these encounters look like in terms of Feynman diagrams. They're not particularly helpful in terms of actually calculating the possible outputs, but they do really nicely break up the sort of internal physics of how these encounters change as a function of total energy and the impact parameter. But unlike, of course, field theoretic calculations, these are actually real encounters with real intermediate states. So we can just solve the result of these three-body encounters with numerical integration. So what I'm showing right now is actually what happens if I throw an interloping star at a pre-existing binary. So binary is going to come in, interact with the field star. And what happens is I essentially get several sort of close passages between the binary and the field star, until eventually that field star is going to eject one of the pre-existing members of the binary, and the encounter is going to terminate with two things changed. First, if you look sort of at the outgoing particle, the semi-major axis of this outgoing binary is actually smaller than the binary that came in. You can actually show that on statistical average, that's always going to be the outcome of, on statistical average, that will be the outcome of these kind of encounters. Binaries are going to come in, they're going to lose energy due to the third body of interaction. And that loss of energy is going to preferentially shrink the binary and produce a new binary with a smaller semi-major axis. The other thing that happens is that energy has to go somewhere, right? And so in practice, that energy is actually dumped into the recoil of the single object and the binary object from this encounter. So binary and single come in, they interact. I produce a new binary with a more negative energy. And to conserve energy, the new binary and single star essentially shoot out at an even faster velocity than they came in with. So what this looks like in terms of the actual cluster is that the binary is going to lose some energy due to this three-body encounter. It's going to shrink its semi-major axis, and the binary is going to get ejected out into the halo of the star cluster. Now, once the binary is out in the halo, dynamical friction will slowly bring it back into the center, and this process will essentially repeat again and again, preferentially shrinking the binary each time and sending it out onto a further excursion to the even farther reaches from the center of the cluster, excuse me. And so at each one of these interactions, the fate of this binary is essentially a competition between two timescales. There's the timescale for the gravitational wave mergers to occur. So literally just how long does it take for gravitational waves to drive this binary to merge? And there's the timescale between successive binary and single encounters. So how long on average is this binary going to go in the cluster before it interacts with another object that's going to shrink its semi-major axis even more? Now, if the gravitational wave merger timescale is significantly less than the encounter timescale, sorry, go ahead.
Yes, I have a question. So we know that at least for field, or if you have field stars, for the masses that you are talking about, they mostly come in doubles or even triples or quadruples. So if you're in this cluster, is that also typical? And how does that affect, I guess it affects the stellar evolution that you will have. How much will do you think that this will change?
Yeah, so we've looked a little bit at how initial binary fraction, as we call it in body parlance, affects sort of our results. And essentially what it changes is how many initial binaries do you have before you start actually undergoing interactions with third objects that can produce some of these mergers. In practice, what happens is that if I start off a cluster with, say, 100% binary fraction for the massive stars, which is typical for what we expect just from observations of massive stars in the galaxy, then what happens is a lot of those binaries will either dissociate just due to supernova kicks or stellar winds. A lot of them won't, and then I form binary black holes. But what happens is these encounters that I just showed, right? They're formally chaotic. So like they will actually completely erase the initial conditions of whatever binaries you start off with. So essentially what happens is whatever initial conditions I started off with are completely erased by the actual dynamical processes themselves. So I essentially end up with two populations from the star cluster in that case. I either end up with the primordial binaries that may manage to evolve to emerging binary with no dynamical interactions, at which point they look exactly the same as binaries from the field or from galactic fields. Or I end up with something where the initial conditions have been completely erased and I'm left with something that is purely the result of dynamical encounters. Now I should say that's particular to globular clusters because of their mass and relatively large escape speed. If I look at smaller clusters like open clusters, then typically speaking, I can have maybe just a single encounter that sort of partially changes the orbital dynamics, but doesn't actually completely erase it. And in that case, you end up with this weird hybrid between binary stellar evolution and dynamics, where you essentially are relying on binary stellar evolution from these like binaries and triples and so on, but some of the processes are interrupted and changed by dynamical encounters. But I'm mostly going to be talking about globular clusters and things in that mass range today.
Okay, thanks.
Sure. Let me just zoom back up. So if the gravitational wave merger time scale is less than the encounter time scale, then the binary is going to merge in the cluster. On the other hand, if the gravitational wave merger time scale is larger than the encounter time scale, eventually what's going to happen is one of these recoils is going to have such a large velocity that it's essentially going to kick it completely out of the cluster. And so one interesting thing about that is that one of these two every binary black hole in the cluster is essentially going to have one of these two things happen to it. Every binary black hole that's sufficiently energetic to begin with, what we call a hard binary, is either going to eventually merge inside the cluster or it's going to be kicked out of the cluster from one of these gravitational encounters. And the nice thing about that is because that sort of time scale is set by the escape speed of the cluster or the central gravitational potential, more massive clusters require more encounters to eject the binaries from the cluster, giving you a larger fraction of in-cluster mergers and a larger fraction of binaries that are ejected from the cluster that will merge within a Hubble time. And so it's a very nice sort of product of these sort of chaotic dynamical encounters. But it's actually the escape speed of the cluster that determines the semi-major axes of the binaries that are ejected. More massive clusters means more in-cluster mergers, just because you have a deeper central potential well, and the binaries are more likely to merge before they can escape the cluster. And this is very nice too, because you can even make pretty solid predictions for what the semi-major axes of ejected binaries are as a function of the initial cluster masses. So this is actually taken from my PhD work, where we basically showed that you get a nice log normal distribution of binary semi-major axes. And the only thing that changes is that the median of that log normal distribution basically decreases as you increase the mass of the cluster. So as I increase the number of particles in the cluster, I'm deepening that central potential well, and I'm preferentially requiring more and more compact binaries to be produced before they can be ejected from the cluster. And that's actually pretty cool, right? Because it means even though this is a formally chaotic process, I can fundamentally predict the semi-major axes and the overall properties of these binaries from a cluster as long as I just know its central escape speed to begin with. It's essentially all gravitational dynamics. There are no dials or free parameters, certainly not like what we see in the common envelope evolution. It's all just well understood gravitational dynamics. And in fact, if I go back to this picture here, where I was showing what the original common envelope merger rate estimates were going back at least 30 years, if I make the same plot, but for rates of mergers from globular clusters, I end up with something that looks like this. It's much more tightly constrained, and the rates are basically all consistent with having a merger rate of about 10 per gigaparsec cube per year. And that goes back to the first estimate that I know from this channel back in 2000 by Porteous, Swart, and McMillan. And essentially every technique going forward has had a merger rate prediction that is somewhere in that ballpark. And these are all using, and a lot of these are using very different techniques. There are direct in-body simulations, there are analytic calculations, there are large-scale Monte Carlo in-body simulations, and they all roughly produce the same merger rate. Another thing that's very interesting is that the largest uncertainty in this is actually just the number of globular clusters itself. So how many globular star clusters do you think there are in a specific volume in space? And so one very interesting thing about this is if you look at that sort of last data point there, it is actually possible, because of this overlap, that globular clusters could explain all of LIGO's binary black holes. The other nice thing about this is, unlike the common envelope channel, we know that the rate can't actually be zero. And I'm going to explain why that actually is in a minute. So if we go back to this picture here, this is a plot that I've taken from the LIGO Virgo collaboration. I've actually left the citation off of it here, which is unfortunate. But you'll notice I've made a couple of changes to it if you know this plot. And the one thing that I've added are these sort of red black holes, the radial velocity black holes. And these have not honestly been sort of as widely recognized in the field as I would have expected. But of these radial velocity black holes, 3 of them were actually identified in a globular cluster. So this is the globular cluster NGC3201. And they've now identified in this cluster essentially 3 black holes whose existence has just been entirely inferred by the radial velocity of their companion stars. And so what happens when you have a large population of black holes in a star cluster is the following. Essentially, the natural tendency of a star cluster is to undergo what we call core collapse. The central regions will move inwards, and the outer regions will expand outwards to sort of compensate for the thermodynamic evolution of the cluster. So my star cluster is collapsing inwards. But if I have a large population of black holes in the center, what actually happens is that these black holes themselves actually provide an internal pressure that counteracts the force of this gravitational collapse. It's essentially the same process you see in stars, right? Like your star undergoes gravitational collapse, you start fusing heavy elements in the core, and the radiation pressure from that releases enough energy to hold the star up against collapse. In the star cluster case, what's actually happening is that internal pressure is provided by the binary black holes themselves. So every time I have one of these 3-body encounters that I was talking about, oops, sorry, I went ahead one too many. There we go. So every time I have one of these 3-body encounters that I was talking about, essentially it liberates some of the potential binding energy of the binary, translates it into the recoil energy of these 2 objects. That's essentially adding energy back to the cluster, and that is where we get the internal pressure that holds the star cluster up against continued collapse. And of course, the problem is, much like you eventually get to hydrogen depletion in a massive star, you're eventually going to deplete your population of black holes. And as that happens through these 3-body encounters where you're kicking them out, then what you undergo is a sort of final collapse of the cluster, which is what we would call a traditionally core collapsed globular cluster. So these are clusters whose surface brightness profile essentially appears to rise all the way up into the center, taking on essentially a power law as they approach right into the center of the cluster. And so what I'm showing here is a plot from Kyle Kremer from a couple of years ago, where he was specifically trying to model NGC3201, looking at the binary black hole, at the black hole population in there. And what he noticed was that essentially to get non-core collapsed models, you need, or non-core collapsed globular clusters, you need to retain a significant fraction of black holes in the center of the cluster. So in this case, this is a model with the only ones that fit the surface brightness profile for NGC3201, which are the sort of blue dots here, are models that have more than 200 black holes at the present day. If on the other hand, the cluster has kicked out all of its binary black holes, then essentially you can't fit the sort of large core profile that we see in star clusters like this. This behavior seems to be pretty universal across star clusters. And it turns out that essentially to explain any of the core collapsed clusters, you have to start off with a sufficiently compact cluster that it has already ejected all of its black holes by the present day. Now, roughly speaking, about a quarter of globular clusters that we see in the Milky Way are core collapsed. And what that means is that they have all ejected their black holes by the present day, and they've ejected them preferentially through the formation of black hole binaries. So that's how we get to the fact that there's a strong lower limit in the merger rate from globular clusters. We know there are numbers of globular clusters, and we know that they have to have some of them have to have compact enough initial radii that they will actually kick out all of their black holes by the present day. And so this fact alone tells us that at least some of the binary black holes from the LIGO Virgo catalog have to have come directly from star clusters, because they have to be out there and they have to be merging in order for this process to make sense. Okay. Any questions about that so far?
Yes. So last I remember hearing was that something between 1/2 and 1/3 should come from this channel. Is that still consistent with the data?
Yeah, so there's a few different studies that have looked at this. I'm on a couple of them. And I'm actually going to get to that at the end. But so we know that this process has to operate, and we know that this process has to produce at least some amount of what LIGO and Virgo have seen. That doesn't tell us, of course, that all of the binary black holes are coming from clusters. And to do that, we actually need to do a much more careful job of the sort of cosmological formation and evolution of these clusters, which actually ties into what I was going to start talking about next. So I think I'll actually just go ahead and move on to sort of the next set of slides.
Thanks.
So, yeah. So what we had tried to do initially, the one thing we're missing from this picture is a good model for star cluster formation across cosmic space and time itself. Like, we don't really understand well how, we don't really use in our initial studies of these globular clusters a realistic sort of formation history for these objects. We don't use realistic distributions of binary black hole, of star cluster initial conditions. And so we don't really have a good sense of how realistic these results are when placed in a more accurate understanding of globular cluster formation. Of course, the problem is we don't actually have a good understanding of globular cluster formation. It's a famously hard observational and theoretical problem. But we can still make a little bit of headway, starting with cosmological simulations and semi-analytic cosmological models. So what I'm showing here is a plot from a paper by Karim El-Badri, where he looked at the evolution of the formation of star clusters in merging galaxies and how you can essentially build up star cluster populations that we see at the present day through the standard hierarchical merger process of galaxies. And so I was talking with Avi Loeb at some point, and we decided it would be interesting to try and combine this model with some of our globular cluster models, our sort of in-body models that are taken from that I'd been generating for the past few years, in order to essentially make predictions for the LIGO-Virgo merger rate. And so we did this back in 2018, back when the Z=0 merger rate was still 50 per gigaparsec cube per year. And so we could play the game at the time of, if we assumed what we had found for globular clusters was essentially the actual answer, how many other formation scenarios would I have to add in order to add up to the full LIGO-Virgo merger rate? And so if I add in globular clusters, I get this nice merger rate as a function of redshift. If I add in triples, it looks something like this. And what we did, which was a little bit cheeky, was we basically said, all right, we have pretty good estimates for globular clusters and triples, moderately good estimates for triples. I wouldn't say they're very good. But if we take these two, globular clusters and triples, as sort of, the truth of God, and we can basically say, all right, what would the contribution of the field have to be in order to reproduce the local merger rate as observed by LIGO, which at the time, for one of their population models, was this uniform and log number of about 32 per gigaparsec cube per year. And so we essentially came up with this, which gave us a pretty good indication of what the merger rate would look like as a function of redshift. Now, this is very interesting for two reasons. One, the merger rate right now can be probed out to about z of 0.7 or 0.8. So we can already start exploring the slope of this curve in the local universe. The second obvious reason why this is interesting is that these proposed next generation gravitational wave observatories, like I was saying, they can potentially detect black holes mergers out to like z of 10 or maybe even 20, depending on the masses. So theoretically speaking, by the 2030s, we might be able to measure this entire curve over redshift directly, which would be a very, very cool thing to be able to do. And so this is what this looked like after comparing to the initial LIGO results from 01 and 02, which was about circa 2018. Come 2019, or however, during 2020, LIGO released the results of their third observing run. And we decided to zoom in a little bit and compare those results to what we were getting from this original study. So I'm zooming in here in the local universe from redshift of 0 to 1.5. And I'm showing a couple of different plots from using this sort of combination of semi-analytic globular cluster formation model with our in-body star cluster models. And I'm showing just the fits calculated using my original models and some more up-to-date models that Kyle Kremer had created. And when the LIGO-Virgo merger rate was announced in sort of late 2020, the plot looked something like this, which was very interesting, right? Because if you look at this, it now looks like both the slope and the overall shape are consistent with what we were getting from globular clusters. And in fact, if I break this down, you could actually explain the entire LIGO-Virgo merger rate just by picking the right combination of star cluster initial radii. What I'm showing here is how the merger rate would change as a function of virial radius if I assumed that every cluster, globular cluster, had an initial virial radius of one of these radii over here. And so we wrote a fun little research note about this and put it up on the archive. And so, at least by the rates, it actually looks like that every binary black hole that LIGO has seen could come from a globular cluster, which is a very interesting thing to be able to say. But of course, that's only going by the rates, or the local volumetric merger rate, which is a very, very famously unreliable measurement. And so if you actually look at what this looks like, I was originally getting very excited by this until, of course, you look at other data coming from the LIGO-Virgo catalog, at which point the answer appears to be no. Every binary black hole is probably not coming from a globular cluster. And the reason we know this actually has to do with the black hole spins that we've measured so far. So what I'm showing right here is sort of the waveform of a binary black hole. And I'm assuming both black holes have initial spins that are aligned with the orbital angular momentum. So black hole spins are in red, orbital angular momentum is in cyan. And then as I rotate the spins down into the plane of the binary, you'll notice that the gravitational wave both changes from its original configuration, and it develops these weird amplitude modulations. These amplitude modulations actually come from the precession of the binary itself, the entire system, about the total angular momentum in gray. And so what's happening is the binary is essentially precessing as a simple system around the total orbital angular momentum. And as the binary is face on, you get a larger amplitude of gravitational waves than when it is edge on. And so essentially the precession of the binary is directly encoded into the gravitational wave itself. Now, unfortunately, LIGO is not that sensitive to amplitude modulations. What it is very sensitive to, because they're preferentially measuring these sort of shifts in frequency, is the actual change in the length and the frequency of the gravitational wave. So what LIGO can measure very well is what happens is the difference between a spin-aligned binary and a spin anti-aligned binary. And so now I'm going to continue to rotate these spins until they are anti-aligned with the orbital angular momentum. Excuse me. And even though I no longer have the amplitude modulations in the waveform, I now have a significant frequency shift between the two systems. Actually, did everybody see the? Yeah. Did everybody see this actually continue to being anti-aligned? My screen's acting a little wonky.
We did.
Yeah, we can see it. A bit choppy, but
okay,
it's there.
Okay, awesome. And so we can make predictions for what the spin orbit misalignment looks like as a function of formation channel. So if I start off with with an isolated binary, even if the spins of the stars start off initially aligned, they can still be torqued off of that initial alignment. And the primary mechanism to torquing these is actually the stellar supernova kicks themselves. So when when the star undergoes a supernova, it preferentially ejects material in one direction, and that can essentially torque the binary angular momentum. At this point, the binary evolves along its normal common envelope channel, and I'm left with a binary black hole with some amount of spin orbit misalignment. And so we can make pretty good predictions for what this spin orbit misalignment is going to be as a function of supernova kick and binary separation. But it still turns out that most of the time you expect the binaries from LIGO the binary black holes formed from binary stars to have misalignments that are roughly around 0. Oops, what happened here? Yeah. On the other hand, in dynamical formation, essentially these things are being completely randomized in space. And so I essentially expect isotropic distributions for the spins and the orbital angular momentum. And so my angle between the orbital and spin angular momentum is essentially going to be isotropically distributed on the sphere. And so we wrote a quick paper about this in 2016, where we essentially argued the following. Because LIGO can measure the projection of the spin onto the orbital angular momentum, which is a parameter they typically call the chi effective parameter. It's just the mass weighted combination of the spins projected along the angular momentum axis. Because LIGO can measure that very well, you should essentially be able to measure the contribution of dynamical formation simply by counting up the number of binaries that have some amount of spin orbit anti-alignment. So at least some component of the spins that are anti-aligned, that are misaligned from the orbital angular momentum by more than 90 degrees, and multiplying by 2. And we argue that that would be a fairly compelling way to ascertain exactly how much of the binary black hole population is contributed by dynamical formation. And so there were quite a few papers that had been written about this. Yeah.
So yeah, I understand, or I think I understand the argument you're making. However, again, let me ask, so if you just look at this paper from 2012, where they claim that most massive stars are formed in binaries that interact, then that would be a direct result, or what you are saying would be a way of saying this. However, if you look at more modern papers, what they find is that as you increase the masses and the population of black holes, which you are studying, has preferentially large mass, which may be an observational bias. But if you do that, you notice that these are in the range where triples are probably the maximum, and maybe even quadruples are starting to be interesting for those masses. So if you have that, then the evolution that you have in a triple can be such that you could have completely inverted spins. So it would be, what I'm trying to say is that it would be much more random for these systems than just what you can or safely assume with a binary.
Yeah, so I completely agree with that. And I'm thinking of that paper, which I think is the one you were referencing, from Max Moe, where he argues that once you get up to the masses of things that produce black holes, your typical massive star has on average 2 companions. So your typical massive star is at least in a triple.
Right.
And so you can make predictions. I don't talk about it I don't think I have these slides in here, unfortunately. I've done some work at some point on what the spin distribution from triples would look like. And unfortunately, I don't have it in this talk. But what you basically end up seeing is the following. If you assume you have a long-term hierarchical triple and you're going to undergo Kozai-Leidov oscillations, essentially what happens is that your spins start off this way. The orbital angular momentum starts oscillating back and forth due to the Kozai mechanism. And at some point, usually your binary is preferentially going to merge when it's about at 90 degrees. And so you actually preferentially produce binaries that are either positive or mostly misaligned by 90 degrees. The peak is around essentially 90 degrees or maybe 70 or 80 degrees. Now that's for stable hierarchical triples. Of course, you're talking also about sort of unstable non-hierarchical triples where you have just like resonant encounters and like strong encounters. In that case, I actually don't have a good sense for what you would expect for the initial spin orbit misalignment. And I think that's a little hard. I think the reason people haven't really written that many papers about it is because you have to, at that point, have a good model for the initial spin alignment of the stars themselves. So the biggest fallback of this paper that I wrote in 2016, and in fact, most of the analysis since then, I would actually say is that we start off with the assumption that these stars have spins initially aligned with the orbital angular momentum. And I mean, there's some symmetry reasons why you could argue that should be the case, right? These things are all forming out of a single collapsing giant molecular cloud, and it's all just one sort of, turbulent region that's collapsing to form these stars. But I don't think we have any good, I could not, for instance, definitively say a priori that that's actually the case. And of course, if I start off with stars whose spins are not aligned with the orbit initially, then this entire picture goes out the window. So unfortunately, when we start talking about initial spin alignments, they get into the very, very nasty, or not nasty, but very, very difficult field of star formation, and particularly binary star and star cluster formation. And that, unfortunately, I just don't think we have good enough evidence yet, or a good enough understanding of yet to say really what the spin alignment should be.
Right, right.
Did that,
I was
did that,
thinking,
yeah.
yeah. I was thinking if you have, I agree that if you have a binary which is initially closed and in a hierarchical system, then this assumption or this guesstimate is not a bad one. However, you still have to go through a couple of kicks, through maybe one or two common envelopes or mass transfer episodes. You still have to interact with the triple, which may be through COSE, but it could also be through mass transfer in several possible ways. So all of these things can mess up this alignment in one way or another, and could give you probably something that's closer to random. I'm not saying that it will be, but it could happen. And also, if you get into the unstable interactions, then it's even even messier than that. So in a sense, that would be one of the caveats that I see to the previous conclusion you were giving, because you have triples, and we are not even talking about more or multiple systems to go beyond triples, right? So and also mergers could come into the picture. And if mergers are, for example, two binaries, right, then a lot of the angular momenta will come from the orbits, and if those are not aligned properly, then the spins could be whatever you want them to be. So I'm just saying
exactly that,
yes, there's a big caveat or a big if there, if you want. That's all.
Oh, I completely, I completely agree. And it's a little unfortunate. So I can simultaneously, with a little bit of ego, say that this initial paper that I wrote in 2016 became a pretty, for better or worse, it kind of became sort of the standing belief in the field, at least from LIGO, so much so that LIGO is now using this for their analyses. Unfortunately, I feel like I didn't do as good a job basically illuminating those caveats when I was writing this initial paper, because this, like, I wrote this right after the first LIGO event, and because it just sort of immediately popped into my head. And unfortunately, since then, there's been this, it's gotten to the point where LIGO has now so much started to believe that aligned binary means it's coming from the isolated binary evolution, that I've actually gotten yelled at by members of the LIGO collaboration for basically saying, no, I wouldn't actually trust my own previous result that much, which was honestly pretty funny. But like I was saying, LIGO has used this for better or worse, with maybe not as many caveats as they should have had, for their analyses. And what they found is that only about 27% of their binary population is consistent with having a negative chi-effective. Now, I'm phrasing this in a way that is, bolsters the stuff I've worked on, which is dynamical formation. And so if I multiply that by 2, it basically suggests that anywhere from 25 to 93% of binaries may be formed dynamically. But you can also reverse that process, right? Or that procedure, right? And argue that anywhere from 7 to 75% of LIGO's binaries actually preferentially have some amount of spin alignment. And so what that actually suggests is that there is some asymmetry in the LIGO data that preferentially is producing binaries that have spins aligned with their orbital angular momentum. And so what this, but in either case, what this result from LIGO itself is actually arguing is that isolated evolution could be nothing, or it could be maximum 75% of the contribution by virtue of the spins. Dynamical formation can't explain everything, but at least by the rates, it has to be at minimum about 10% of the contributed LIGO-Virgo detections. By spins, assuming you believe that isotropic argument that I made, that minimum goes down to about 25%. But either way, what we are forced to conclude from this is that there are probably multiple formation scenarios at work, and that what we really need to do is disentangle these theoretically into different populations so that we can perform actual astrophysically motivated gravitational wave inference, using preferably all the same self-consistent physics. And so I'm going to end just by talking about one paper by Mike Zevin that I think might have been the one you were alluding to. And what Mike did for this paper was actually take 5 different formation scenarios from the literature, some of my own work on globular clusters, some work on nuclear star clusters, and 3 different formation scenarios for isolated binary evolution. He might have actually included triples. I can't remember if I gave him that data or not. And what this plot is basically showing is the contribution to the LIGO Virgo population as a function of birth spin of black holes for dynamical channels, so globular clusters, nuclear star clusters, etc., versus isolated binary channels, or things that occur within the field. And so it turns out to fit different mass features and different spin features. You need to make assumptions for the birth spins of black holes. But what he basically argues in this is that unless the black hole spins are extremely large, something like 40% of the detections are likely coming from anywhere from 40 to 75% of detections are coming from the dynamical channels. And he can make a much more solid statement, which is that no channel contributes more than 70% of the binary black holes that we've seen so far. And so I'm going to go ahead and stop there because I'm at the hour, but I'm happy to answer more questions if people have them. Otherwise, thanks so much for having me.
Yeah, thank you. And does someone have questions? I mean,
I do if no one else has.
Okay, Aldo.
I just read a paper from Keister, Farr, and I think it was Renzo, talking about how to explain this 25% of negative effective binaries
that's from
isolated.
Tom Callister's paper?
Yeah, exactly, that one.
So there was one they put out where they did something crazy, right? Which was they basically said, because what you can do, right, is you can argue that, assuming this is the paper you're thinking of, you can basically argue that if you have incredibly large supernova kicks and they're in just the right direction, yeah, then you can produce line systems, which is definitely true. Like if I assume, and we even did this back in the 2016 paper, if I assume that black holes get the same kicks as neutron stars, which is this dotted cyan line here, then something like 10% of isolated binaries will have spin orbit misalignments that are greater than 90 degrees. Just because essentially the supernova kick actually reverses the orbital velocity of the binary and you get a negative spin orbit misalignment. Of course, if you do that, the binary black hole merger rate from the isolated channel tanks. And I think if you were to actually make the assumptions in the Callister paper for those, for the kicks they needed to explain that asymmetry, you basically can't reproduce the merger rate of binary black holes. I don't think they said that explicitly in the paper, but I'm almost certain that that's true.
Yeah, I remember just saying that they need like thousands or more kilometers per second in the kicks just to get these things to actually work with the rates.
Yeah,
they seem LIGO. So it was a bit crazy.
That paper was, yeah. Well, in their defense, the way they were thinking of that paper was basically as a proof by contradiction. So they were basically saying is, all right, if we can show that isolated binary evolution isn't everything, because if it was, then you would basically need this incredibly large kick in order to actually explain the spins that we're seeing. And since that massive kick is basically impossible, then we conclude that isolated binary evolution isn't everything. The kick they were saying you needed was, I think it was like 4 or 5 times the neutron star kick velocities. It was some absurd value.
Yeah. Thanks, Carl.
So these kicks, are you talking about the momenta or the velocity?
That was the velocity.
Okay.
Yeah, they were looking
Yeah.
at velocity.
Right, but that's not necessarily a good way to go, because you have objects which are 20 times the mass of the neutron star, right? So you
Yeah.
so if what you are getting in a supernova is a certain amount of energy and then a certain amount of momenta, then you would expect an equivalent kick to give you probably 20 times less velocity, I guess.
Yeah, and that's what we actually do when we're normally generating these populations. We actually assume that the initial kick is taken from the same distribution as neutron stars, and then we scale it down according to the amount of mass that falls back onto the newly formed black hole. So they are essentially momentum conserving kicks. So in our simulations, when we're trying to do this realistically, we actually do get kicks that are typically much, as you say, 20 times smaller than the neutron star kicks. What they were basically arguing was that, you know, they made no claim that the 2,000 kilometer a second kicks were physical. In fact, they claimed that they were essentially absurd. What they were claiming was that if you wanted to explain the spin orbit misalignments with kicks alone, assuming everything started off with initially aligned spins, then you'd have to have supernova kicks this high, and that they assumed those kicks were essentially were completely absurd.
Okay, all right. So I have one more question. I don't really have much of a sense of what's the stellar physics that you have in your models. I have some idea of what goes on into something like StarTAC or COMPASS or this population synthesis.
You're stealing my question, Enrique.
Okay. So good for me, or do you want to do it yourself?
No, continue. I was going to ask about COMPASS and all that. How much do we trust them? How much does Star trust them?
Well, we, in a sense, we already know that we shouldn't trust them very much, in the sense that they are using 1D stellar evolution, and there's many things which are not included there. So I would like a sense of what's the physics that's actually included in your code, or code similar to yours. I guess Sambra Banerjee's might be another one of those. So what's besides the physics of the interactions themselves, which you already mentioned, what's the stellar physics which is actually included there? Because even just the core collapse can have lots of we don't really know how those things work, in a sense, and we know that they shouldn't be 1D, and many of these things are using 1D. So how much of this can be included?
Well,
Thank you.
I would actually say that it's somewhat worse than that, because they're not even doing 1D stellar evolution, right? They're using almost every PopSynth code out there is using these original fitting formula that were developed by Jared Hurley 20 years ago. Ironically, they were actually originally developed for globular cluster simulations. They were in order for us to better resolve the interaction, the sort of collision rate and binary evolution of things in star clusters. This was 20 years before people were thinking about binary black holes. And essentially, they were all polynomial fitting formula to a bunch of different quantities from old EZ stellar tracks from Chris Tout. And they're not BSE, which is the code that all these were based on. This is what COMPASS uses for its stellar evolution tracks. This is what Cosmic uses. This is what MobC uses, what StarTrack uses. The code is very good for what it is, but it was never designed to be used for 100 or 200 solar mass stars. And in fact, if you keep extrapolating, because it's at that point, you're essentially using polynomial extrapolation from stellar tracks that were only tuned from 0.5 to 50 solar masses to do your actual massive stellar evolution. So it's actually much worse than just being 1D stellar evolution. It's 1D stellar evolution that is done by polynomial interpolation or polynomial extrapolation from some polynomials that were only interpolated up to 150 or to 50, excuse me, solar masses. In terms of what we're using in the code, we actually, if you have one of these, so what I was working on for the past year or so was our first public release of CMC, which is this cluster Monte Carlo code for stellar dynamics. And as part of this, what we ended up doing was essentially integrating at the sort of GitHub repository level our own sort of BSE plus a bunch of other stuff code, which is called Cosmic, into CMC. So these are now essentially linked at the repository level, and any sort of binary stellar population synthesis you do with Cosmic can use the exact same stellar physics as whatever we use for our Monte Carlo simulations in CMC. Now, there was already stellar evolution in CMC, so it wasn't really a huge amount of labor to put it in there. It was just making sure that these two sort of versions of BSE were synced up and using the same sort of assumptions and physical prescriptions. And so essentially, this allows us to do sort of apples to apples comparisons between isolated binary evolution and dynamical formation, and look very specifically at what the difference is between these populations. Now, of course, you have to actually trust the population synthesis, which is a whole nother problem. Like, we have basically all the same assumptions in there for massive stellar evolution and stellar winds and compact object formation and core collapse that, say, Star Trek or COMPAS do. But, you know, then the question is, do you actually trust those prescriptions? To which I would just sort of personally shrug and try to change the subject. And so
Right.
that's sort of where we're at right now. The nice thing is, once I have my initial population of black holes, then I'm done. So really, I only need to get stellar, like some initial population of black holes in order for the dynamics to sort of take over. And at that point, everything is very well understood with basically no free parameters or dials to tune. But obviously, there's the assumptions of, you know, how do you map massive stars into black holes in the first place?
Right. Okay. Diego, do you want to keep going with this question?
No, that was it very much.
Okay, so just to continue with this then. So one of the things that you wouldn't know, for example, is what's the extent of the envelope of a star above 40 solar masses. So any interaction between anything and a red giant or a red supergiant is actually a question mark.
Yeah. I mean, I can tell you precisely what Cosmic and CMC do in that case. I would not pretend that it's actually a physically reasonable thing to do.
Right. Okay.
Yeah.
All right.
I mean,
Okay.
it's all prescription-based physics, basically. So you kind of, you sort of map what's in there and hope for the best.
All right. Okay. Great.
There are, yeah. One thing I'm a little excited about is people are starting to work on next generation population synthesis approaches, where instead of using these like interpolation formulas and simple prescriptions, you can either generate large tables of, for instance, MESA binary evolution runs and use machine learning to interpolate between those, or you can replace the sort of polynomial interpolation from BSE with new tracks and essentially interpolate between those stellar tracks. So you could imagine, for instance, instead of just adding a new stellar wind prescription on top of what's already in there, you could actually adjust detailed physical questions about the stellar evolution tracks themselves that are used for the evolving these stars. Like, for instance, if you wanted to, you could go mess with the reaction rates or the mixing links parameters, you know, the things that actually control 1D stellar evolution codes, and then start doing these population synthesis and dynamical models with those new stellar tracks, just sort of dropping them in. So I'm really excited to see where this goes in the next few years. And I also just want to say briefly, like, BSE, the original code for this, is actually an extremely well-written code for what it does. The real problem is that all of us have been using it for things well outside of the ranges it was ever designed or claimed to work well for. And so it's really just that we're running this code that was, you know, designed basically to look at white dwarfs in star and collisions in star clusters, and we're using it to model 200 solar mass stars and
Right,
common envelope physics.
Right. No, that's one of my worries, because indeed I mean, the population that you showed at the beginning has these 30 plus solar masses, black holes predominantly, and that usually comes from stars which are above, let's say, 70, 80, maybe 100 solar masses, and we don't really understand that. There's even this paper from Balchinsky in the last 6 months, maybe even 3 months, which precisely tells that, brings it. I was surprised that that actually someone using these codes was saying these things out loud, because
I was surprised. I was
yeah.
surprised at it too, because the paper basically argued you shouldn't trust any of my previous results because
Right,
they're not trustworthy. I was so
right,
surprised to see that in a paper.
right. No, and in a sense, I was always arguing these things. We don't really know what's going on with stars above 40 solar masses, especially with these 1D codes, and even the prescriptions that they're, or the tables that they're using for population synthesis are really iffy, because they're coming from these
Yeah.
other codes, which are also iffy for those masses. So what do we really know there, and what can we actually tell? And then this paper comes out. I was like, okay, finally they're starting to say it out loud. Yes, so
Yeah.
interesting. Yes.
Yeah, which is why, that was also around the time I sort of changed up my talk to really emphasize the fact that, at least from a dynamics perspective, the globular cluster and other dynamical formation scenarios are, they have much less uncertainties. The dynamics we actually understand very well and can make very good predictions for. Of course, you still have to get the black holes there in the first place.
Right.
But
Yeah. And right there is
Yeah.
part of my question, because if in a cluster you also have formation of a triple, then what you could expel originally is the triple, and the one that becomes bound is not as bound. So you could keep expelling the visitor and actually form something like a binary in the center, right? So how in that sense, I would also like to drive my question from, I don't know, 40 minutes ago. So how trustworthy are this original population that you form inside a cluster?
So I would argue that it's basically, because what happens is a lot of the times you will shred the pre-existing binaries and dynamically dissociate them, that a lot of times you're actually saved by the fact that most of the binaries we see from these were just dynamically formed, and or they underwent at least one strong encounter, which was enough to completely erase their sort of initial conditions.
Right.
What is you have to be careful about, though, is that you still need to get the initial black hole mass function correct. For that, we're assuming that, Cosmic, our population synthesis code, is taking us from Krupa IMF to initial black hole population in a way that is reasonable. Our prescriptions are up to date with the best ones in Star Trek and everywhere else, but that doesn't mean they're right. It just means they're
Right.
the latest prescriptions.
So and I don't want to to make all the questions, but there's one last important question that's bugging me here. So they keep going at the spins, and I understand that the spins are easy in a sense to track because of this modulation. But one thing that would make that would probably be a stronger case for dynamical as opposed to a binary or even a triple system is eccentricity, right? With dynamical, you have no way of removing the eccentricity. So in a sense, you expect them to merge with eccentricity. Whereas in the other case, you had all these common envelopes and all these other tidal interactions, and a long time to use these tidal interactions to get rid of eccentricity. So how hard would it be to extract that from the signals that we're getting from the gravitational wave mergers?
So in the previous versions of this talk, I used to actually talk a lot about eccentricity, because it turns out, so all of the signals from all the binaries from clusters are produced with some eccentricity. And in fact, some significant fraction of them, the eccentricity needs to be very large to be detectable by LIGO. Basically, these things have to get all the way into the LIGO band, so seconds away from merger, and they still need to have an eccentricity of 0.1 or greater in order to be detectable by LIGO. However, if you include post-Newtonian effects in these dynamical encounters, you can actually create gravitational wave captures, which then retain some of that eccentricity up to the present day. Unfortunately, I apparently have taken those slides out of this talk, so I can't show the nice movie that I usually have that points this out.
Okay.
But something like, it turns out that if you do this, that if you use these sort of post-Newtonian equations of motion, something about 5% of the binaries from globular clusters should have eccentricities that are detectable.
Hmm.
The problem is unfortunately a completely different one, which is that it is extremely difficult to detect and pull that out of the waveform. And it's because we don't actually have good post-Newtonian waveforms for what eccentricity looks like. We have some that are starting to get there, but the amount of work that went into the circular templates, especially with different spins, is like an order of magnitude greater than the amount of effort people have put into eccentric waveforms. And right now, we actually don't have, I don't think LIGO has any eccentric waveforms they can use for parameter estimation that have both spins and eccentricities. Now, there's been some claims in the literature that there have been eccentric mergers detected so far. Oh, and I do actually have one of my plots here, so this is good. So this is from a paper I put out a couple of years ago where we added for the first time these post-Newtonian terms into our star cluster simulations. And what you're looking at on the x-axis here is the eccentricity at 10 hertz. So roughly speaking, when the binary enters the LIGO Virgo band. And so these gravitational wave captures occupy this very high eccentricity space up here, and about 5% of them are actually eccentric enough to be detected by LIGO. Now, the plot on the left is actually from a paper by Isabel Romero Shaw, where she did a reanalysis of GW 190521, that really large black hole with masses in the masses in the parent stability mass gap.